Now for homework of section 6.3, which is on page 578, please do problems 117, 121, 125, 29, 31, 33, 41, 45, 47, 54, 55, 61, 63, 71, and 73. And when you're finished with the homework, come back and I want to talk about them. Now that you're done with homework, let's look at problem 125. Now the 125, I believe you're just supposed to calculate what is Pn of x. In this case, n is just 1, okay? So then you just plug it in and things come out pretty nicely. The same with the remainder estimate. You plug it into the formula and everything will come out quite conveniently like this. I will show you here. See the first we write out what Pn is. Pn is just the Taylor series, but only up to the end point, and only n terms. And then here's the remainder, which I repeated here. And remember what m is. M is the maximum of the n plus one derivative of f for the interval that is between x and a. So then f of x is that we calculate P1 by plugging in the formula, maybe take the derivative, I guess, yes. And then you come up with some value, and this is correct. And then next, we follow the formula for the remainder, figure out what the maximum of the m has to be. Being that x is between 27 and 28, x equal to 27 would cause the maximum to happen. And then you calculate that equal to something that's I guess on the seventh, on the seventh position, the 7th degree. Actually, where did I get that? Well, it doesn't matter. The point is, when you plug it in, here comes the result. Okay, it's pretty straightforward. That's problem 125. 129, we are supposed to work on the natural log of x. So then we have to do the same thing, right? And so 129 is basically the same kind of principle, I guess. What happens is that we follow the formula that except the 129, we have to go all the way to n goes to 1,000. See, before we only picked n equal to 1. So we went from 1 to 1,000. And so you have to write out 1,000 terms. Well, we're not going to actually do that. That's just theoretical, right? So you have a function, and you have to somehow figure out n equal to 1,000. But first, let's figure out if there's a pattern to the derivative. And come to find out there is. See, if you work on it, eventually you realize that the derivative at 1 follows a set pattern of that thing, which means the Pn of 2 is, well, 2 is what we are trying to evaluate because x equals to 2. But before we get there, actually, even as we get there, because x is 2, okay, a is 1, so x minus a in this formula is just 1, which makes your Pn of 2 much better. Okay, when you write it out, then you realize that it equals to this particular formula, where, you have minus 1 to the power I minus 1 divided by I. Now notice that I changed the variable from I to n because n is a fixed number in the Pn formula. So you have the counter variable, which is I, you need to use a different counter so as not to confuse yourself. So using I as a common one for the index, and then that gives you what Pn is. And then we're able to sum it up to a very specific formula. And then, okay. And then when n equal to 1,000, okay, at this point, okay, now that we have a specific formula come up, we no longer have to write this thing out to 1,000. We simply type this summation into the calculator, the decimals calculator, where the summation symbol is typed as SUN, and write all this stuff in. Once you type it in, n equal to 1,000, then the calculator will give you this number. And then when you calculate natural log of 2, you notice that's a different number, and the difference is less than 1,000. Okay, that's the real difference. And so that would be the end. So I guess the neat part of this problem is that when you calculate Pn, you are actually able to come up with a clean formula that represents it from 1 to whatever n you want, even if it's 1,000. And therefore, you don't have to do some math to 1,000 to come up with the answer. That is not necessarily possible, okay? But this problem is an easy one, and so things worked out nicely for us. And then the next thing we have to do is calculate the maximum error, which we follow the error formula, which is that thing. I wrote it down again. And then you plug it in and figure out what, being that the number has to be between 1 and 2, and your maximum formula turns out to be something like this, then the bottom, the maximum would be at when z is equal to 1. So then you notice the maximum is limited by n factorial. Now, if that is the case, that number grows fast, okay? If you don't, remember the n factorial, if you weren't told earlier, when you first learned, n factorial grows fast, okay? Your average calculator can only handle n factorial up to about 70, okay? Beyond 70, the number is way too big to handle. So n equal to 1,000 is your average calculator won't even be able to tell you what it is. So then the point is, however, that so the m is huge. However, you can still plug it into the error the remainder calculator, and it luckily cancels out pretty nice, so that your error end up being controlled by 1 over n plus 1. So then it equals 1 over 1,000 plus 1, which is slightly less than 1 over 1,000, which is what we are required to do. The n equal to, so that's why this thing, your book wants you to calculate n all the way to 1,000, and that only gives you like 3 decimal places accuracy. That's because the Taylor series doesn't necessarily work well with everything. See, sometimes it converges nice and beautifully, like in the sine case. In the natural log case, it converges extremely slowly. So it'll take you 1,000 terms before you get to even a reasonable amount of accuracy. That's the way it is. So next, problem 131. We are supposed to do the e of expansion and then turn it into the e to the power minus x squared. Now to do that is we find the Taylor expansion for e to the x itself, and then simply plug the e to the minus x squared into the Taylor series for e, and then everything will come out very nicely. For example, let me show you what I mean by that. First, we figure out what the e's expansion is, okay? E's expansion is just that thing I wrote down. How do I know that? Because it was done in example 6.112, which is part of your homework. Okay, so that's where you pull that back out. You don't have to do it again. So that's e. So what happens to e to the minus x squared? Then you plug the x minus x squared right into the Taylor expansion where x used to be. Okay, just stick the whole thing in there and then clean it up a little bit, and then you come up the expression for e to the power minus x squared that quickly. And then you write it out a few terms, okay, until actually the book specifically wants you to write out 6 terms, which is these 6 terms, right? And then you plug it into your integral calculator, or do it by hand. Doing it by hand isn't that bad, but the calculator is maybe faster. It depends on how fast you can type it in. So you put it in the calculator and then add it all. Oh yeah, the calculator is better because if, I don't know, maybe this is okay, because this you will be adding it in the calculator anyway. So either way, you're going to be able to come up with this answer, okay, once you do the integration. This I just used the definite integral calculator, and then out pops this answer. You can I also typed it into the original, just typed in the original problem into the definite integral calculator, and it gave me that other answer, which, as you can see, is slightly off by the 1, 2, 3, 4, 5, the 5th decimal position, which is so the approximation is very, very good, and it's extremely close. Yeah, so that's that. Next, problem 133. F of x is just cosine x, and the we're trying to expand it from minus pi over 2 to pi over 2 with a equal to 0. So what are we doing? Oh, we're just trying to calculate the remainder. So what you do, plug it into the remainder formula. Now in cosine's case, as you remember, the cosine's derivative just goes to sine and then cosine and sine again and all that. So then the maximum it can reach is just 1. So you plug 1 in there, and then this thing, when is this thing going to be less than 1,000? That is not going to be easy to calculate because you have n plus 1 factorial down there. So what I did is just typed it into the sequence what is it called? Plotter. The sequence plotter, which I have the link in this below this homework. Below this video, okay, in the homework description. And so you can just type that into the sequence plotter and plot the whole thing out and see where it approaches 0. Okay, this thing has to be less than 1,000, so it's approaching 0, and see where it gets close enough to be less than within 1,000th of 0. And it'll get there very quickly. So I eyeballed it from my plot, and it turns out to be n equal to 7. At n equals 7, the remainder, I mean, that is, yeah, the remainder, which is the error estimate, is down to something like that, which is less than 1 in 1,000, because that's the 4th position, and 1 in 1,000 is the 3rd decimal position. So that satisfies the requirement. And yeah, next. Next, 154. I guess we're supposed to develop the Taylor series of natural log of x. And we have done some of it already in the previous problem 120, I don't know, 9 or something. Doesn't matter. We'll just do it again. So you follow the formula, and everything turns out pretty nicely. And until at the end, watch out for at the end. Because of f, the first term is 0, okay? So when you do your summation, do not start at 0. So you start at 1, because the first one doesn't exist, and in starting at 0 won't make any sense. So starting at 1, everything will work out. And once you get here, after some kind of work, then you realize the formula looks like this, and then you cancel out the n minus 1 factorial with the n factorial, and that gets you just n on the bottom, and that's the formula for the natural log. And we're going to need that formula later in problem 171. Next, let's look at problem 161, which says that, okay, we have a summation of 2 to the power n over n factorial, and they want you to come up with a Taylor series. And how are we going to do that? Well, we're going to look back at the few Taylor series we've done. The first one is, of course, e to the power x, which is in some example. I didn't even write down which the example we've done that. And example, well, whatever example it was, okay, is one in the examples which we calculated e to the x equal to this thing. And therefore, when you compare this thing with the problem, you know that x equals to 2. In other words, if you have e, this is the expansion for e when x equals to 2. So then the book wants us to calculate the first 10, S10, or something like that. All right, so we calculate S10 by typing this summation thing into the calculator, and then it comes up with that answer. Now, if we actually just punch in e squared, it comes up with this answer. As you can see, the two numbers are very close, okay? And that's the 10th approximation. The two numbers are off by at the 4th decimal point. So that's very good. All right, so that's 161. 163, same thing. We have this thing right here, and if you look at the example on page 566, I have it written down here. I think the E example is in the same spot. Doesn't matter. The point is, you look for the sine example. You notice that this is identical to the sine example if you let x equal to 2 pi. All right, so we plug in 2 pi, and sine of 2 pi is 0. We know that. And then the other one, well, what about the 10th, n equal to 10 approximation? If you plug this thing into the calculator, and you get something over here, I have a mess here, I don't know why. But anyway, as if you can see it carefully, it has 4 zeros and then 8 in the 5th position. So the approximation is quite good. That's like what? 100,000th position. Okay, it's accurate within 100,000, that sort of thing. All right. Next, let's look at problem 171, which is an interesting thing to do, I guess. And they want you to calculate the limit with the help of Taylor series. All right, so let's try that. First, we see some complicated natural log limit problem. Okay, well, so then what we're gonna do is first we'll use the result we got from 154, which says f of x equal to natural log of x. The Taylor series looks something like that, all the way down here, see? And once we know that, then that's natural log of x. Okay, what about natural log of not just x, but a bunch of stuff, 1 minus x squared? We'll plug the 1 minus x squared exactly into the x, okay? And then and keep the division of x squared in here, see, right here. So everything is accounted for. And so for the summation, then and remember, n start at 1. So, well, whatever. So the point is, then we do the summation and then clean stuff up a little bit where, let's see, did I clean stuff up? Yeah, because eventually, what you get is, what you get is that you have 2 minus 1s, okay? And when you multiply them together, you add up the coefficient, it becomes 2n minus 1. Minus 1 to the power 2n minus 1. 2n minus 1 is an odd number, always. So therefore, minus 1 to an odd number is always minus 1. So all that minus 1s turn out to be just minus 1. And once you figure that out, then you divide out the x, and then you let x go to 0 in this, and well, you can write out a few terms, right, just to see what it looks like. If x goes to 0, the only thing you got left is minus 1, which is the right answer. So that's that. Okay, now 171, and then the last problem is 173. The same principle, okay? We're supposed to calculate the limit of some kind of cosine. Well, the cosine on page 565, you already did the homework, which gives you the cosine equals to this thing, okay? It's part of the example on 565. Now, once that's true, we will plug things in one step at a time. First, we'll subtract by 1. If you subtract by 1, then the first term here is 1, okay? If you put n equal to 0, and stuff is 0, 0, 0, etc., and the only thing you have left is 1. So the first term is 1. And so if you subtract by 1, then the summation simply starts at 1 instead of 0, see? So so the sum looks the same, except the n start at 1. Yeah, pay attention to that part. See, that's because it's subtracted 1. Okay, so that's that. Next step, we're going to replace the x with square root of x. So you plug the square root of x into the formula, so then you got rid of the 2 up here. So you only have x. The next step, we'll divide everything by 2x. Okay, so I divided by 2x, and then I clean it up a little bit, and it becomes something like that. Remember, n is still starting at 1. So then, so I got here, and then the rest is just let x equal to 0. If you let x equal to 0, this is a series where everything else, all the powers of x that's 1 or bigger is going to disappear, right? So only the first term exists, and the first term is minus 1 over 2 times 2, because there's a 2n here. So then it becomes negative 1/4, which is the correct answer, and that marks the end of this section. And is this also the end of the chapter? No, maybe not. Never mind. This is the end of this video.